Hello, everyone. My name is Chao Li. I'm a research scientist at AIP Center, RIKEN Institute. In this presentation, I'm going to talk about the notion of tensor network, and we'll focus on its model selection problem, which is new and crucial to affect the performance of tensor network in the application of machine learning. The studies on the tensor network are mainly motivated by the problem called dimension exposure, which happens almost everywhere in the field of machine learning. So to address this problem, we borrowed the idea of tensor networks from the field of quantum mechanics and found that the tensor network is a promising framework to deal with high-dimensional problems in machine learning. Well, so in this presentation, I will first give a brief overview about tensor networks and its application in machine learning, and then we will talk about the targeted problem in this presentation, the problem of tensor network structure search, and at the end, we will give our solutions to this problem to show how to find the optimal tensor network structure via random sampling. Well, let's start with the concept of the tensor network. The definition of the tensor network relies on a fundamental mathematical object called tensor, which is intuitively a multi-way number array. In the context of tensors, we can consider vectors as tensors of order 1 because there's only one index for locating their entries, and consider matrix as tensors of order 2 because there are two indexes corresponding to rows and columns. And here, when we say tensors, we commonly mean the ones with higher orders. And then on tensors, we further define an operation called contraction, which can be understood as a natural extension of the matrix multiplication. The tensor contraction amounts to the tensor multiplication. And to simplify the notations, tensors and contractions can be also represented by graphs. Here, we use the vertices with multiple downlink edges to represent tensors with different shapes. So based on these concepts, the tensor network is thus defined as an edge-labeled graph, of which the vertices correspond to tensors and each connected edges indicates the contraction between the two linked vertices. So we can see the tensor network can be used to describe a sequence of complex contractions among many tensors. Well, now we know what the tensor network is, so let's move on to the next question, how to use tensor network in machine learning. Suppose we have a learning equation as shown in the slide, where x is the input, y is output. The w here denotes the learnable parameters, and the phi indicates any nonlinear functions requiring the learning task. This learning equation is so simplified, but still can be used to describe a wide range of learning tasks. And in this science, the problem of dimension exposure usually implies two things. The first is the dimension of W here is literally high. It means that we have to pay much computational resources for training or for the inferences, which might not be afforded. And the second thing is sometimes the dimension of W is not so high, but the size of the training set is very limited. This situation usually happens in the field of scientific research, and in this case, we usually suffer from the series overfitting problem. So to resolve these problems due to the dimension exposure, the recipe of using tensor network is very simple. There are only two steps. In the first step, we need to map the high-dimensional parameters into a tensor space, and we call this step as tensorization. And then we will find a suitable tensor network to decompose the high-dimensional parameters into a group of low-dimensional blocks connected by the tensor contractions. Because the tensor network has a significant ability for model for the dimension reduction, so the two-dimensional problem will be mitigated. So to further understand this point, let's see one example that is the problem of tensor completion. The goal of tensor completion is to predict the missing values of a tensor from the observed entries. And it has been successfully applied to the tasks such as recommendation system and image painting. And we know that the tensor completion problem also satisfies the mentioned learning equation. But in this problem, the x are coordinates of the entries, y are values of the entries, and the w here correspond to the completed tensor, which is our target. And the function phi is usually just the identity, and sometimes it's a reshaping operation. And in practice, we usually have to be faced the situation that is only very limited entries can be observed. So the tensor completion usually suffers from our fitting problem. So to resolve this problem, what we did by tensor network is just as what we have mentioned. The high-dimensional parameters will be replaced by a low-dimensional tensor network. Here we use a tensor train format corresponding to the path graph, for example. Because we have known the tensor network can be used to describe a sequence of multiplications of the low-dimensional tensors. It means that this trick can successfully transform the high-dimensional original problem into some low-dimensional latent space. And so, as the result, our fitting problem will be solved. And the tensor network also has rich applications in deep learning. And the goal in this application is mainly for model compression. We can see that in the existing works, various tensor networks are applied to different deep neural networks. But on this point, we should note that even though in their works, they show that the tensor network gives remarkable performance for model compression, but there's still no principle to show if their use of tensor networks are optimal for their tasks. In other words, there's no answer for the question how to select optimal tensor network structure for the machine learning tasks. So this factor motivates a study of on the problem of tensor network structure search, or TNSS. The main goal of this problem is to looking for the optimal tensor network structures for machine learning tasks. And this is a relatively big problem which covers three specific subproblems. They are the rank section, permutation search, and topology search. To understand the meanings of these three problems, let's see another example. In this example, we try to represent the fMRI data by tensor networks. The fMRI is a sort of brain images which are naturally are tensors of order 4 because there are 4 physical indexes, where the indexes x, y, z correspond to the spatial space which contains our brain, and the index t correspond to the time space. So for the first tensor network rank section problem, here we are looking for the optimal H labels, which determines the bound dimension of the vertex tensors. And because these labels can be also concerned as the tensor network ranks, so this problem can be understood as an extension of the classical rank section problem for matrix decomposition. And for the next tensor network permutation search, here we seek the optimal mappings from the tensor indexes to the vertices of the graph, because it's equivalent to find the permutations of the vertices in a graph. So we call this problem the tensor network permutation search. And for the last one, the tensor network topology search, it's very obvious. Here we are looking for the optimal network topology, such as the circle graph, path graph, or trees for our representation task. Well, there have been many methods which can be used to solve these problems. If we consider the three mentioned problems as the three different directions for the whole tensor network structure search, there's a special area where the tensor network structures are fixed, because in this case, the problem becomes the trivial application of tensor networks to machine learning. So there has been lots of works here. And studies on the rank selection are also rich, because it's close to the rank selection in the matrix case. The studies on the topology search is relatively new, which is firstly mentioned by Hayashi in 2019 and formally proposed by us in 2020. And following our works in the recent years, some methods were proposed where they focus on searching both the ranks and the topology. And at the end, for the problem of the permutation search, the study on this problem is very new. It was formally proposed also by us just in this year, but actually, this problem has been conceptually discussed by tensor researchers for a really long time. And in the most recently, Chen and their co-authors from Duke University theoretically proved that the optimal permutation for tensor train and tensor ring is identifiable. And the involved techniques in these algorithms are also different. In this presentation, we will give our solutions to these problems via statistic search. We choose this technique because it is more flexible to deal with the variety of the learning from the different learning models or different learning criteria in practice. Well, to introduce our solutions, let's begin with some mathematics. As the first step, we need to formalize the tensor network structures. Here in our methods, the tensor network structure is modeled as a simple graph G with its H labeling function R, where the graph G contains the information about the topology and the permutation, and the function R corresponds to the tensor network ranks. And and we use the explicit definition of the tensor network proposed by Ye and Lam in 2019. We choose this definition because it highlights the importance of the tensor network structures. So based on these frameworks, the tensor network structure search for the decomposition task, for example, as to solve an optimization problems as like this. Here, the objective function can be the compression ratio or the number of parameters which is used to evaluate if a tensor network structure is good or bad. And in the constraints, the graph set GC and the rec function set FC determines the feasible set of the tensor network structures in the search. And if we can construct the feasible set with different forms, we will obtain different searching problems. For the rank searching problem, we fix the graph by looking for the optimal ranks. And in the permutation search problem, we construct the graph that as the set of graph isomorphisms so that we can search the optimal permutations of the vertices and the topology will be preserved. And for the last topology search, we usually fix the tensor network ranks, but consider all possible simple graphs in the search. And in our algorithms, we try to seek the optimal tensor network structure via random sampling. And the key point is to give a good balance between the exploration and exploration in the search space. And our algorithm mainly contains two phases, that is sampling and evaluation. In the sampling phase, we randomly draw a batch of tensor network structures with some learned sampling distributions. And in the evaluation phase, each tensor network structure will be given a score to represent its fitness in the problem. And all the informations of the scores will be used to update the sampling distribution for the next iteration. The two phases will be done recursively until convergence. And more specifically, our methods consider two sampling tricks. They are the global sampling and the local sampling. The global sampling means that we draw the samples from the whole search space. Well, for the local sampling, it means that we only sample the structure from some predefined neighborhood for some given point. And as for the updating rules of for the sampling distribution, on the global side, we apply the well-known genetic algorithm, and on the local side, we concern the zeroth order optimization. It means that we use the samples from the neighborhood to estimate the steep-based descent direction to update the sampling distribution. And the two different sampling tricks have their own advantages and disadvantages. It's difficult to say which trick is better because it's just a different balance between the exploration and exploration. Well, next, let's see some numerical results. This experiment is for the natural image compression using the tensor network topology search. And the goal is to looking for the optimal, the most efficient tensor network topology for this task. And here we randomly select 10 natural images from the open access dataset and consider two performance measurements. The first is compression ratio and second is relative squared error. And for comparison, we take the tensor train and the tensor ring as the baselines, which are the two most popular used tensor network in machine learning. And from the experimental result, we can see with a similar approximation currency, the topology search algorithm always achieve a better compression ratio performance. And we can also see that the optimal tensor network structure learned by our algorithm is significantly different from the ones used in the existing literature. And the second experiment is for the tensor network permutation search. Here we applied our permutation search algorithm to 3 benchmark experiments. There are image compilation, image compression, and dimension reduction for Gaussian processes. And here we also evaluate the computational efficiency between the global and the local sampling trick. The values in the squares is the number of required evaluations by the algorithm to achieve this performance. It determines the computational complexity of the algorithm. We can see from the experimental result that the local sampling requires a significantly less number of evaluations to achieve a similar performance as the global one. To verify this point, we also check how the loss function decreased by the two algorithms with different number of evaluations. And we can see that for the local sampling, that is the red line, that is the red line, the loss function decrease consistently faster than the global one with different settings. So we can say that the local sampling is more efficient than the global one for the tensor network permutation search task. Well, at the end of this presentation, let's have a brief discussion about why tensor network structure search is so important. It is because the tensor network structures encode our inductive bias about the learning task. And the efficiency of the tensor network for machine learning also comes from here. Because of the flexibility of the tensor network structure, we can encode as much as our prior knowledge about the task into the models. But this prior knowledge can be encoded into the ranks or the graphs. But the problem is, in practice, it's quite challenging for us to know how to encode these inductive biases into the tensor network correctly. So as the conclusion of this presentation, we'd like to say our research results prove that these inductive biases can be learned from the data set efficiently. Thank you.
Okay, thank you very much. Are there any questions?
Questions for Chao here?
So then let me start. So
yeah.
Structure search is of course a quite important problem, but always search cost is really sometimes exponentially high. Right?
Yes.
And this time you focused on evolutionary strategy, and this is maybe practically useful. But can you somehow say how scalable the current approach is?
You mean the stability?
No, scalability.
The scalability. Yes. I think maybe this is depend on what kind of sampling strategy we used. If we consider use the global sampling trick, it means that the genetic algorithm is used. In this case, maybe the algorithm can only deal with the tensors with orders less than 100. But we can consider the local sampling trick, means that we only draw the samples from smaller neighborhoods. And then we estimate the kind of gradient-like directions to update our search strategy. In this case, maybe the algorithm can deal with the problem maybe more than hundreds.
I see. So that means if you have some prior knowledge or some hint to focus on a particular local region, then your method can be scaled to a larger part. Okay, thank you. That's clear.
Yes.
Today, I'm going to talk about our recent paper, mainly, which I just like called offline reinforcement learning via symmetries of dynamics, which we also presented at the ICML this year. It's with like Sam and Animesh from the Vector Institute in Toronto and my PI here, Yoshinobu. So just quickly, like we have heard about it, but like that slide is mandatory. So in a reinforcement learning setting, we have an environment in which the agent can take actions, right? And it observes the reward and observation with this action. And then usually, as we have seen also before, we have that the agent is composed of a critic, which evaluates, you know, how good is this data mean, how good is my observation, and like what is the best action to take, which is then given by the policy of the agent. Right, so I'm mainly going to talk about offline RL today, which uses a static training data set. And in particular, that means that further environment exploration is not possible, right? So we call this framework Koopman Q-learning, because we learn a Koopman latent representation, which from them we infer symmetries of the dynamics of the system. And we then utilize the symmetries to extend the data set. Right, so here's a very simple example of the mountain car, right? So the car has to reach the top of the hill, and it actually has not enough power to do that. So it has to oscillate forth and back, right? And so let me turn this. So this is just like an illustrative example, right? So we plot trajectories from expert policy, and we see that all of them reach the goal on the top right, after some certain time. And you can see that even for the simple example, which is a one-dimensional example governed by an ordinary differential equation, the state space, or even for the expert policy alone, is quite, well, complex. And so we can transform these observables in actually in a 5-dimensional space. So below I show projections, like 3-dimensional projections in the Koopman observables, and we see that in particular on the right side, it's like, it says all different perspectives of the same thing. We see that it's like a circle, right? So the dynamics then given by the Koopman operator, which is a linear operator acting on the Koopman observables, basically amounts to rotation here on the right side. Right, so symmetries, right? We just like very briefly, they appear everywhere in nature. Here we have the rotation and the mirror flip. Those are global symmetries. But today we're going to mainly talk about local symmetries. Well, this is just like a figure here, right? So local symmetries can be very different as the global symmetries. Here would be, for example, a local approximate shift symmetry, right? Comparable to the global mirror flip. So in particular, so I'm going to be very rare with formulas today. So, but here's one. So the symmetries we're talking about are actually local Lie groups, and they basically have to obey the 3 properties that there's an identity element, right? That they can be composed, like either way, so that's commutative. And also like they admit the Taylor series expansion. That means for every point locally, I can like write the symmetry shift as like as a linear shift in epsilon, with some function theta of s. Right, so why is this important to us? So what we will find is that, so if that is again like the state space of the environment, and like this black line here is a trajectory from the initial condition Ti to Tf, right? So let's say imagine it's an expert policy acting on a state space, and this will give you this trajectory in the in state space in the environment. So the offline data set obviously contains this information, but we are very limited, right? So it would be nice to have like an elaborate way of generating new data, which is like with some high reliability, like resembles the dynamics of the original system. And this can be done locally by this local symmetry shift. So you can just imagine, in fact, it shifts like the trajectory locally to a nearby trajectory with a different initial condition, right? So all of these trajectories still are governed by the same dynamics of the system, which we of course don't know in general, right? So we have to learn it. Right, and so those trajectories are not contained in the original data set, and the idea is that providing more data to the algorithm during training then will enhance the performance. So how do we approach this, right? So it's actually quite simple. you just have to pre-train like basically this variation autoencoder, which has the additional feature that it is basically just if you take the identity map on the latent space, you get just ST, so the same state. However, if you want to apply the linear operator, which is the Koopman operator, which is just like a matrix multiplication on a latent variable, you will get the next state, so the state in the next time step. And the ansatz for the Koopman operator, as I said, is just linear. Here's a K0 and Ki are just matrices, and AI are the actions taken, right? And what we actually find, so this is the theoretical result, is that you can get a symmetry transformation or a symmetry generator. So sigma is a symmetry generator if and only if it commutes with the Koopman operator, right? So commute means, K times sigma minus sigma times K equals 0. And then, as I mentioned before, as soon as we have the symmetry, we can take a data point, which here is again like we take ST plus 1 and ST, right? So it's actually 2 points in this high-dimensional state space, and we can transform along different symmetry directions, right? Because we're not going to only find one symmetry, we're going to find in generically different symmetries. But however, to stay numerically stable, we restrict this to like an epsilon ball region around the original data point. And we will then generate, as I said, like these new valid data points in this epsilon ball. So let's make a sanity check on how well the algorithm performs. So on the top left, you see D4RL, which is a benchmark data set by Fu et al. And we just plot one of the, I think this is like maybe medium expert, one of the trajectories from medium expert data set of the Walker. And there's been some paper which the authors call S4RL, in fact, our collaborators, where they randomly shift the state space and see that already just like random augmentations, even along this continuous action space, leads to a performance in the results, in the reward function. And however, you see that like it's quite like, it doesn't really resemble sometimes the dynamics. However, on the bottom, you see our symmetry shifts, like with small and large, basically epsilon ball region shifts. And like the shifted state looks very much like the original dynamic, right? So let me say here, like it's supposed to be jumpy because we shift every data point with a different like symmetry direction and symmetry magnitude, right? So it's not expected to be another smooth like running Walker, but rather that basically every frame transition, so from one frame to another, looks reasonable, which it very much does. Right, so what we can also do is like, although the algorithm only uses local symmetries, we can just make a check if like actually our approach can also recover global symmetries. And we just test this on the card pole. And in fact, like the global translation symmetry is naturally like derived or is learned in a self-supervised fashion in this Koopman latent representation. So the way to use that is like, so we put our framework on top of CQL, which is conservative Q-learning, which is the state-of-the-art for model-free reinforcement learning with several modifications. And we only modify the policy optimization step. And in a very naive way, we just modified the Bellman error with the symmetry shift here, where E is the Koopman space embedding. So it embeds the state space, the continuous state space variable, into the Koopman observable. And then we apply the symmetry shift. So we again shift by epsilon ball. So we take the identity plus the symmetry generator, right? Which gives us this local Li group acting on the Koopman observables. And then, of course, we have to take the inverse embedding to embed back to the state space, which can then be used for training. And epsilon here is a normally distributed random variable, just like it has been proven empirically useful, not to use that as a fixed parameter, but introduce some randomness here. That's why also like in the expression above you see S twiddle D conditional from ST plus 1. That means basically the probability only comes from this random variable here. And we call this framework Koopman forward conservative Q-learning, or short KFC. So like very briefly, so the empirical tests, we perform a wide range of experiments. In fact, we test our method on the entire D4RL dataset. And you can see here the ant maze. So in the top left, it's very small, but I hope you can see it. The ant has to find the way in the maze. Then, of course, the mutual code tasks, which are very familiar, like the walker and half cheat and so on and so forth, but also like the Franca kitchen and the Adroit tasks. And moreover, we perform robotic manipulation tasks as well. So the benchmarks are famously the RoboSuit, and which the robotic arm has to manipulate certain objects. And below is like the meta world tasks, right? Where it's very similar. But we don't perform the meta experiments. We just like see if our algorithm can actually learn the dynamics of this process and how well it performs. So so the empirical results of the KFC and what we call KFC++, which are just two different ways of getting. So the difference between KFC and KFC++ is the way the symmetry transformation is derived from the Koopman operator. And you can ask, I can tell you later in detail how that is done, but it's basically just like two different algorithmic ways of saying, okay, I have a matrix, right? I know the matrix and I want something which commutes with this matrix, basically, right? And we see that like, while S4L actually has improved CQL last year to be the quite significantly, we find that KFC and in particular KFC++, again, in average give quite a improvement over CQL and S4L respectively. And so briefly what I mean here, so the task name, I mean, like when I say chum, I mean all the mutual code tasks, right? So this is an average over all the data sets, which is, for example, the replay data set. So every environment like the Walker 2D has like different data sets, right? It has the random one, it has the medium expert one, it has the medium one, it has the replay buffer one, and like the average of all tasks, right? And the score here is the normalized score. So roughly 100 is for every environment is basically what you can possibly achieve. And right, so yeah, and the same for ant maze, we average over all different data sets, and for Adroit and Franca, and we find that the score is improved. For the meta world and the RoboSuit environments, however, we only take very specific tasks, which I list here. For the meta world environments, we tested on the push, the door close, the sweep into, and the reach wall environment. And for the RoboSuit, the big place scan and the block lift. So only two, in fact, right? So where the robotic arm has to do like two different tasks. And in green and blue, we have again the KFC++ and KFC, and we see the same pattern, right? So KFC++ is always a little bit better than KFC, and is better than CQL. In plus S4L, which are the random shifts, right? So they have one variant of it which performs the best, and we have taken this as a baseline here. So concludingly, we actually find that our method improves the state of the art of the model-free reinforcement learning, like quite consistently over this wide range of tasks. So I've been intentionally brief here with the first part because I wanted to spend the second part on giving a little bit like an idea. So what we're working on right now, and what is the motivation behind the research we are doing. And so what we've done here in particular is to provide a method for out of distribution generalization, right? So like the symmetry transformations give you a reliable way to generate new data, which are not in original distribution, but which resemble them quite closely. And the hope is, since there's symmetries, it's not a trivial shift, right? It's not something you could get easily otherwise. So there's a different, however, category which people look at, which is varying environment generalization, which for example means I have an end, and the end now has to carry a pack back, right? Or is heavier. And how well does my algorithm adjust to these kind of changes? And there's, maybe the biggest challenge here is task generalization, in which we learn that the robotic arm, for example, has to learn how to pick up a block, and then without telling it the new task, it has to learn how to, I don't know, open a door, right? Something completely different, which obviously is not covered in this work. So again, so here the first category we addressed with these coupon representations. It would be interesting to apply this to model-based RL, right? That's something we've been thinking about. And so let me come to the generalization to varying environments. So what people have done is, for example, they have added like wind, right, to the end, or make the legs longer or shorter, right? And then there's this other one for games in particular. You have the same, well, it's basically the same distribution, but you sample for the training set and for the test set, you sample from, right, for different parameters of the same distribution, basically. So you see that the background is different, like the objects have different color. It's like different, maybe like structure. And the benchmark here is the Brocken benchmark, which has been quite interesting. So, and it turns out, surprisingly, image augmentation is all you need for those tasks, right? So, and when I say image augmentation, I mean really naive, like the standard, like cropping, translation, rotation, cutout stuff, right? And to achieve generalization, at least for, for changing background color, like those image augmentation has performed quite well. However, the pitfall is that it over-regularizes due to the naive augmentation methods, right? So here's like just like a plot taken from the Laskin et al. Paper, from the Hansen and Wang paper, which gives you the mean and Q error for different augmentation methods. And I think this is for the walker, so it will even vary for the environment, right? And here you see this the same thing, right? It's just like a different graphic. You see on top you see the Brocken environments, jumper, star-botted, big fish. On the bottom you see the test environment, so the training versus test environments, just like to give you an idea. And on the right you see like how different augmentation methods perform, right? And I'll give you a second to look at it because of it. So the baseline is the black one. So you see some of them in fact perform just better, and something even worse than a baseline in a training process, right? So where the time steps are in millions. And the basic state of the art to approach this is to say, okay, I'm using a selective way, right? I'm kind of self-supervised to learn which augmentation method is best. And like we're approaching this challenge a little bit different. This is a collaboration with Rishabh Agarwal at Google. And we try to think of like the idea that inductive bias in a policy network, right, and value network can actually like replace augmentation methods to some extent. And very simple, what we do is we actually have like attention mechanism, which however can be interpreted like as a graph, and we preserve the graph symmetries, right? So graph symmetries, for example, here of the walker would be like translation, so you can shift the graph, right? Or you just mirror it, right? And on top of that, you can rotate the graph, right? Previously we call this graph symmetric attention. I will be very brief here since this is actually work in progress. But the idea is that you get like a latent representation, which then admits certain symmetries, right? And why is that relevant, right? Just like in a simple example of the grid world, right? You can generalize just to say, okay, I instead of, so first of all, the goal here is to get the key and go to the green square, right? So, but what is to say if a turn is around, right? And say, okay, the green square is not in the bottom right corner, but in the top left corner. Right? It turns out that most algorithms will not generalize, right, to the simple naive generalization. Of course, this is just a rotation. So, in a way, like we should be able to do, the algorithm should be able to do that. And in the bottom, you want to generalize to the different, more difficult setting, right? it's called lava crossing, where the orange fields are lava and the agent cannot fall into the lava, but has to find the pathway, and in the end again reaches the green square. Right. So another generalization benchmark, which is quite which is basically like state of the art, is called the destructive control suite, and the goal here is to actually not take the same distribution for the desktop, but it's actually a different distribution. This is achieved by using like a wide set of range of videos, right? So high resolution, relatively high resolution videos in the background, and also shifting the camera angle position, and like during during testing. And it turns out that the current state of the art algorithms cannot even learn, right? So this is training from pixel data. I should have mentioned this, right? Obviously, cannot even learn despite tests on across this like third difficulty level, right? So there's a full set of like, right, there's a wide range for improvement. Right, so I've now covered the middle part, which describes the idea of how to generalize to pixel-based RL, so to varying environment generalization, as like done in these few benchmarks. But like there's something else which we are interested in, which is task generalization. And of course, by that I mean, this is basically meta RL. So there's the inner loop. The inner loop here in this picture describes the normal training process, right? So the agent performs an action in the environment, gets the reward and observation. However, the policy or the agent has to perform a wide set of environments, right? So different tasks. And this is most often done by viewing the different tasks as like a contextual variable, or like this is formalized in a contextual Markov decision process, right? However, it turned out that like it's competitive to this strategy. You can just use meta Q-learning for a multitasks objective, right? So you just say, okay, I'm training my normal Q-learning algorithm on all of these tasks, and it performs roughly comparatively well, right? So it is that kind of like hints to the fact that there should be some room to improvement, in my opinion. And so briefly what I mean by that, so multitask reinforcement learning, that's not what we're talking about. It's like, I don't want to learn a lot of tasks very well, but what I want to do is I want to learn from several tasks and then be able to quickly adapt to a completely new task, right? And although we have tested our previous algorithm already on the meta world, we've actually not done any task generalization, right? Because that was not the goal, not to be confused what we've done in the work I presented in the first part of my talk. But here, right, so again, this is just like to repeat, on the left side, you see a set of tasks. On the right side, for testing, you see a different set of tasks, which the algorithm then should quickly be able to learn without having seen it at training time. Right, so there's like a last like perspective to that, which is there's also generalization to new strategies, right? So this is also something which I would put under the umbrella of meta RL. And this is usually done by a population of N agents which interact in the same environment and are learned from each other. And a famous example for that would be AlphaGo, right? So the two agents play against each other, the Go game, and it improves them. Well, the same agent plays against itself and improves their own strategy. So the critical part here is how to have a meta strategy who guides the learning process, right? And in this population learning framework, the game theoretic perspective has been widely used. And like, in fact, we are working on one approach right now. And mainly we are working on a collaborative one, but of course, in an AlphaGo game, for example, you have like the adversarial approach, right? And of course, you can combine those to get both, right? So to summarize, like the theme of our work, which I presented in the first part of the talk, aimed to accomplish generalization, out of distribution generalization in a continuous control tasks, right? But it is like part of a bigger research like theme I'm trying to follow with several collaborators to approach generalization to also like these other, what I would call other categories of generalization, which is, you know, varying the environment, so varying actually the dynamics of the environment, right, or the composition, like the background color, or even like generalizing to new tasks, right? And in the end, also generalizing to new strategies, how to solve a problem, right? Good, thank you.
Thank you very much. So then Volkan, do you have a question?
Yes, so thank you for the very nice talk. If I understand correctly, in the first part, you talk about Q-learning in a way that is model-free, and you're trying to use maybe invariances, something like unsupervised learning, in order to augment your data and somehow do better. Is this correct?
Yeah, that's a good way to say it. So it's in a way it's a new principled way for data augmentation.
Okay.
So we do not really like make any changes to the CQL algorithm, right? Other than using the augmented data training time.
Okay, I actually like this because I mean somehow you think about even, let's say, encoding the Q function with a neural network, and then somehow by doing these invariances you end up getting something structured with it, right? Is that correct?
Yeah.
I mean, have you noticed if you work with these things, did it lead to convolutions? Did it lead to maybe some architectures that somehow are known to work certain invariances? Did you try some of the practical things?
So this is not really like the invariance of the architecture itself. So what we used for the variation autoencoder, we just use the MLP, right? So there's basically no well, there's no, so the invariances are not invariances of the neural nets. The invariances should be really like part of. So I have like a dynamical system, right, which is governed by differential equations.
So I think that I meant that do the invariances also get reflected in the let's say the function that you learn somehow, which is the neural network, right? Not the vice versa. So you try to enforce invariances in the data, you end up maybe do data augmentation, and then you start training representations. And you know, right now there's a lot of unsupervised learning work with representations. And some of these, you know, I don't know, maybe things like shift invariance result in convolutions and things like this. What I was saying is you also make that connection that in the deep Q learning world, that these Koopman invariances would prefer a certain type of architecture versus another in order to encode these kind of invariances.
Okay, right. So yeah,
that was
so
a too
actually,
convoluted
the question before. Yeah, I've understood the question before, but I wasn't sure like in what way you would hope to achieve that, because like as we said, so I know, for example, that you know shift similarly leads to convolutions, right? So that's actually a little bit more closer to the second part, where is that what we should working on right now, which is inductive bias for in fact for vision transformers, right? But it's it's different from the question, but the invariances are really, those are local Lie groups, right? Okay, so
they're local, yes.
I've not thought about that, but I would not be aware of like any, because this is really a local transformation, right? So we are not looking at global transformations, which might be future work, right? To extend it like to to say, okay, I don't know,
I mean,
the obvious
maybe
global transformation.
somehow you can use the global transformation in the model-based RL case. You mentioned that you're looking into this. Because if you have certain model for the transition dynamics, you can also perhaps encode global invariances along with the local.
Right. So okay, yeah. So what you could do is, so for example, for the Wako 2D, right? So even like for the model free case, so what people usually do, they truncate the position from the training variable, right? So the position, the absolute position of the Wako or half cheat or whatever is not used for the training. And the reason is because it's super confusing for most like Q-learning algorithms, right? Because it's actually completely irrelevant because there's a symmetry and people truncate it. So what you could say, what you could ask is, we have not done that. Since our method self-supervised learns also global symmetries, right? it should in principle perform better if you would actually not naively truncate this from all experiments a priori, right? So that's one thing we thought about doing, but we actually didn't have, well, we don't have any empirical results on that. We didn't do it because it's kind of established that you just you assume it's such an obvious symmetry, right? You just truncate everybody does it, right? Even like the environments themselves, right? If you get the observation, it's truncated, right? So the position is truncated. So that's the one thing. And right, sorry, what's the second question?
Yeah, well, I actually have one more question, if you don't mind.
Sure,
you talked about multi-agent setting.
Yeah.
And I think that you're going to do the lifting on the multi-agent setting. So you, as opposed to looking at individual agents, you would like to find the distribution of, let's say, policies or value functions or Q functions over agents. Is that what you meant at the end? In the multi-agent setting?
Yeah. Here you mean, or?
I think the next slide that you were showing that there are population learning framework, right? And a game theoretic perspective. So did you mean here that you want to learn the distribution over the agents? So population games, there sometimes when you have too many agents, you don't learn individual things, but you learn the distribution over them, right?
But I think they're different.
They're different. Okay.
Right. So I think there are different approaches implemented in the literature. So we are by far not the first people to do that, right? So what people have been doing in I think the original work by Langdon et al., I think it's cited here, is to say that well they consider something like called the response oracle, which is like well it's basically what it does is like it's a normal form game. So each agent plays against another agent, let's say, or like it learns to improve that agent, but it's that the agent itself has not access to the. So I'm just describing it, not a meta strategy, right? To say how the learning process works. And the meta strategy there would be, okay, I let one player play against the other, but I don't give them the full set of options, right? And basically let them say if they at least like if they can extend their options, if they would then be able to improve their performance over this agent. So that's kind of the meta strategy there. And that's what I mean by game theoretic, right? It's really like one agent plays another other. The population, I think, is as soon as you have in that sense, in that paper, is as soon as you have an agent which performs better than the other agent, you actually just say, okay, then I add this to my population, right? It's basically in the pot of agents which perform well, and you just like keep adding agents. But I think I agree what you say. Like there are papers out there which then say, okay, this could maybe be phrased as like, okay, as a distribution over agents, right? I mean,
that's what I was
considering. But it seems very reasonable that people would do that, right?
Yeah. Okay. Thank you very much. Other questions?
Can I also follow up this part? I'm also interested in the multi-agent scenarios, but it was not so clear to me. What was the real challenge here compared to the single agent scenario? Would you recapitulate it again?
So for this case or for this case?
Next page.
Next page. Right. So you mean the challenge here? So
yeah. So you have n agents now interacting in the same environment.
Right. So this approach usually is used for example, for the game Go, right? So you know the rules, but you don't have any. There are, for example, too many options to ever have like a data set, right, to say to train from. I mean, you can do it, but it's not going to perform well, right? So the challenge is like twofold. So the challenge is, okay, well, the challenge for the multi-agent setting, I think, is that so one open challenge is if you have too many agents and you want to optimize with respect to too many agents, basically it just becomes numerically very hard to do, right? That's one challenge, but you're, I think, asking but you're not asking for a technical challenge, you're asking for what is the channel challenge behind this framework, or what is the question?
Yeah, maybe from your perspective.
From my perspective, So from my perspective, the challenge is that well, there have been certain approaches to use that, and most of them use the Nash equilibrium as the guiding principle, which is, Nash equilibrium in a game tells you that if you have two players, that it's optimal for them, so they don't have to change either of them has to change their strategies, right? And that has been kind of the main focus of a lot of the work in the field, right? And a challenge for us is actually want to try something different in a way, to find a meta strategy which is not focused on a Nash equilibrium.
So in essence, in that case, the design of reward function itself is already quite challenging.
In fact, for us, that's actually true. Yeah, but for our approach. But in principle, so the reward function generally is given, right? But if you want to frame something as a collaborative game, you want to, so I'm really talking about the things we are thinking about at the moment, is, so okay, so if you take any game, right, the reward function is given, right? Let's say you play rock, paper, scissors, right? If you win, right, you have the reward function, you get a point, right? But now you could ask the game, okay, so we play 5 people, we play rock, paper, scissors, but in the end, we want to phrase this as a collaborative, so we have a collaborative aspect to this, right? So let's say 3 of us play together for something, right? And then the question becomes, okay, so the reward then obviously has to be distributed with something. It has to have different meaning, right? It has basically a private meaning, so I win something, but also like I share part of my reward. And that's actually a challenge we are facing, because it's not so clear that, like, because that's not given, right? A priori, you have to define it somehow. So in that sense, yes. So you have to define what, if you want to define, basically if you want to apply this method to something, the collaborative setting, which is not intrinsically already collaborative, but you want, so basically there are collaborative settings where the reward function is clear, right? But if you want to basically like apply collaborative setting to a setting where it's not necessarily collaborative, right? It's not so clear what the reward function is. That is true. Yeah.
Okay, thank you very much. That's very interesting.
Yeah.
Maybe we should stop here. So thank you very much.
Thank you.
There is one quick question here, or do we stop? Sorry.
Is there one more question?
There is one more question from the...
Oh, yes, then.
Okay.
Please go ahead.
Okay, I ask a very quick question. What's the difference between the Koppelman scenery and the kernel methods in RIKEN-AIP? Because in my view, after the embedding, both of them, the thermodynamics are linear. So I'm wondering what's the difference?
Thank you.
Okay, I actually don't have the formulas here. So, okay, I do not know a good quick answer to this question.
Okay, then maybe we take that offline.
Okay, thank you very much for the introduction. The title of this talk is a method to construct exponential families by representation theory. This is a joint work with Taro Yoshino. First, I introduce myself shortly. I'm a postdoctoral researcher in mathematical science team. My name is Koichi Tojo. My research field is Lie group theory and representation theory, which is a study of symmetry of spaces. These are my hobbies. Recently, I have enjoyed shogi, which is a traditional Japanese board game like chess. This is more complicated and dynamic than usual chess because we can reuse the piece we captured from the opponent. If you're interested in, please play shogi. Then let's enter the research talk. First, we explain our aim of this research and demonstrate a family of distributions on the upper half plane with Poincare metric so that we can share our aim of this research. One of our aim is to suggest good families of probability distributions on important spaces. Not only Euclidean space, but also curved spaces such as sphere and upper half plane. To attain our goal, we propose the method to using representation theory. Here we demonstrate a family of distributions on the upper half plane with Poincare metric obtained by our method. The right side is the upper half plane with Poincare metric. This is a family of distributions on the upper half plane with three-dimensional parameter space. We want to suggest a good families not only upper half plane. Okay. This is a plan of this talk. First, we will talk about background of our motivation. And next, we will explain the method. We call it G-Motate method here. And if we have a time, I introduce related work. In the field of first, I talk about motivation. In the field of machine learning, learning using a family of probability measures is one of important methods. Here, learning is mathematically to optimize the parameters in the family of probability measures. We often use exponential families as a probability model. This is a good class of families of probability measures. In fact, exponential family are important subject in the field of information geometry and are useful for Bayesian inference and include many widely used families. Family of normal distributions is a typical example of exponential family, and exponential families include Bernoulli distributions and gamma distributions, Wishart distributions, von Mises distributions, and so on. Categorical distribution is a generalization of Bernoulli distributions. Wishart distributions can be regarded as a generalization of gamma distributions. Von Mises distribution is well studied in the field of directional statistics. Here is our definition of exponential family. We modified well-known definition in the field of statistics for convenience to representation theory here. Roughly speaking, exponential family is a family of distributions having this form, with this exponential form. More precisely, here let X be a manifold and Rx the set of all random measures on X. A subset P consisting of probability measures of Rx is an exponential family on X if there exists a triple mu Vt satisfying the following four conditions. The first condition is mu is a random measure on X, and the second condition is that V is a finite dimensional vector space over R, and the third condition is T is a continuous map from X to V, and the fourth condition is the most important condition, namely for any element of P in P, there exists an element of dual space and dual of vector space V such that this equality holds. Where Phi theta is the log normalizer. We call the triple mu Vt a realization of P. Some texts call this triple representation, but to avoid conflict with group representation, we call realization in this talk. Let's see a typical example, a family of normal distributions. This is an exponential family on R. In fact, we can take the realization mu Vt like this. This realization is not unique, but easiest one in the sense of the dimension of V. By definition, there are too many exponential families. However, only a small part of them are widely used, like this picture. Oops, sorry, it is too small to see. Let's enlarge here. Oh, good. There are good exponential families we often use. From this picture, we can expect there exist good exponential families. So we want a framework to understand good exponential families systematically. This is our motivation. The following observation gives us a hint to attain our purpose. Namely, useful exponential families have the same symmetry as the sample spaces. Mathematically, the sample space is a homogeneous space, G mod H, and the family of distribution is invariant under the induced G action. Here, G is a Lie group, and H is a closed subgroup of G. So our idea is to use representation theory, which is a theory of symmetry. Here, writing a space by the form G mod H is a description focusing on symmetry. For example, the real line can be described as a homogeneous space by taking affine transformation group here, which means real line has a symmetry of scaling and translation. Sphere is also a homogeneous space, which has a symmetry of rotation group, SO3. Upper half plane is also a homogeneous space, which has a symmetry of linear fractional transformation of SL2R. We proposed a method to construct exponential families by using representation theory. In this talk, we call it G mod H method. G mod H method has good properties. Namely, the method generates many well-known families, and moreover, families obtained by the method can be classified. So we can expect that new families obtained by this method are good. Now we will explain G mod H method. First, let us see a method roughly. Later, we will explain the method step by step. G mod H method is a method to construct a family of probability measures on G mod H from the following two inputs. One is a finite dimensional real representation rho from G to GLV. And the other one is a non-zero H fixed vector V0 with regard to this representation. Here GLV is a group consisting of all linear isomorphisms of real vector space V. We will see the details of G-Montage method step by step later, but roughly speaking, we take the following 5 steps. In first step, step 1, we take Lie groups G and H. Here H is a closed subgroup of G, and X, which is a G-mod H, and we consider X as a sample space here. In step 2, we take 2 inputs, finite dimensional real representation rho V and an H fixed vector V0. In step 3, we consider the set omega GH of all non-zero relatively G-invariant measures on X, which is compatible with group action. In step 4, we make measures parameterized by direct product of the dual of V and omega GH on X. In the final step 5, we normalize them. Before moving to each step, let us see examples obtained by G-Montage method. Our method generates useful exponential families systematically, like this. In fact, by choosing these input GH V0, we obtain these families. Here, choosing input GH V0 is to give an interpretation of symmetry of the family of distributions. We mark that these are not all of examples obtained by our method. To explain each step of G-Montage method, we would like to apply G-Montage method to construct normal distributions in the top of this table. Now we enter the details of G-Montage method. In the left side, we explain each step in representation theory. And in the right side, we demonstrate how the family of normal distributions is generated by G-Montage method. In step 1, we prepare sample space with symmetry. We prepare sample space with symmetry in the representation side. We take a Lie group G and which describes the symmetry of the sample space, and the closed subgroup H of G, and the homogeneous space G mod H, denoted by X here. In the normal distribution side, the real line R has symmetry of scaling and translation. So we take the corresponding affine transformation group G and its closed subgroup H like this. Here the first component of affine transformation represents scaling, and the second component represents translation. Then we can identify G mod H with real line via this map. We will construct a family of normal distributions on real line with a well-known form. In step 2, in the representation theory side, we give input to generate distributions. We take a finite dimensional real vector space V and representation of G and non-zero h-fixed vector v0. Here G0, GLV denotes a set of all linear isomorphisms of V. In the normal distribution side, we take the three steps like this, respectively. Here, Sim2R is the vector space of all symmetric matrices of size 2. We can easily check that V0 is H-fixed by considering the case X is equal to 0. In step 3, we consider measures compatible with symmetry. In the normal distribution size, a measure compatible with scaling and translation is essentially the Lebesgue measure on the real line. Mathematically, measures compatible with symmetry means relatively G-invariant measure on X. The definition of relatively G-invariant measure is given in definition 2.3. So we consider the set of all non-zero relatively G-invariant measures on X up to positive scalar. We denote it by omega GH. This depends only on pair G and H. We regard an element of omega GH as a parameter later. In step 4, we construct a measure on X with symmetry. More precisely, in the representation theory side, we define measures parameterized by the direct product of the dual of the vector space V and omega GH as follows. Here, rho X V0 is well defined because V0 is H-fixed. In the normal distribution size, by taking normal natural inner product on the space of symmetric matrices, we obtain measures parameterized by real numbers theta 1, theta 3, and theta 3, theta 2, and theta 3. In the final step 5, we normalize the measures above. We denote by large theta the set of parameters such that the measure is integrable on the whole space X. We call it parameter space in this talk. Then, by normalizing the measures, we obtain the set of probability measures P theta parameterized by parameter space. In the normal distribution side, we can compute the parameter space like this and the normal log normalizer like this, and as a result, we obtain the probability measure like this. Namely, we obtain family of distributions on the real line as shown. Moreover, by changing variables here, we obtain the well-known form of normal distributions. Now, we see the properties of G mod H method. The family obtained in this way has good properties. Namely, the family obtained by our method is a G-invariant exponential family on G mod H. For example, in the normal distribution case, G action means scaling and translation. So this proposition corresponds to the fact that the distribution transformed by scaling or translation from normal distribution is also a normal distribution. then the following question 2.5 naturally arises. Namely, are any G-invariant exponential families on G mod H obtained by our method? The answer is yes, under a mild assumption. So we accept the answer, roughly speaking, there is a correspondence between the set of G-invariant exponential family on G mod H and the set of families on G mod H obtained by G mod H method. For details, please see our paper if you are interested in. Now let's see related work in the field of machine learning. Cohen and Waring submitted a paper to ICML, which is a conference of machine learning. Their paper suggests harmonic exponential families on manifolds, on compact groups, or compact homogeneous spaces, such as circle or sphere. And use first Fourier transform on circle or sphere to perform gradient-based optimization of low likelihood for MLE. And apply them to the problem of modeling the spatial distribution of significant earthquake on the surface of the Earth by regarding the Earth as sphere. Let us see the relation, the method by Cohen and Waring and G mod H method. The paper by Cohen and Waring gives a method to construct exponential families on G mod H by using unitary representation of compact Lie groups G and G invariant measure on G mod H. Please remark that the method by Cohen and Waring can be regarded as a case where G is compact of G mod H method. In fact, in the case where G is compact, then relatively G invariant measure is automatically G invariant. So as a result, in the case of where G is compact, the method by Cohen and Waring can be regarded as a special case of G mod H method. We leave take-home messages here. If you want a good family of distributions on some spaces, please tell us spaces. We will try to propose good families of distribution on them. Thank you very much for your listening. These are references.
Okay, thank you very much. Any questions? So then, let me ask a question. So
okay.
I want to somehow draw some practical implication from your results. So can you go back to the final slide and?
Final slide.
Yeah. So this. Yeah. So this new family. So from a machine learning viewpoint, how can we utilize this in like improving a method or generalizing a method?
You mean you want to know the application of these distributions?
Yeah, you could call it application.
For example, we want. I think the family of distributions on upper half plane or more general space such as hyperbolic space is not so many. So by suggesting family of distributions on that spaces, then we can perform the MLE on hyperbolic space or upper half plane. So
in a sense, we can run a machine learning algorithm in a natural way in upper half plane, for example.
Yeah. For example, we can use these family of distributions, for example, meta-learning in the Bayesian setting, because if we consider the family of normal distributions, then we need to fix a prior mean and variance. Then by taking the x-axis as a mean and taking a y-axis as a variance, then we can use these family of distributions for meta-learning.
Have you ever tried any experiments?
But I didn't run experiments. In fact,
yeah, that would be an important future work for you, because
this
is one step further towards machine learning.
Yeah, so I want to we want collaborator, and if we have a problem on the machine learning on upper plane or hyperbolic spaces, then we want to collaborate.
Okay, thank you very much.
Great. So hello, I hope everybody can see my screen. My name is Tomasz Rutkowski. I am from RIKEN-AIP, University of Tokyo and Nicolaus Copernicus University in Poland. And in RIKEN-AIP, I represent the application side. So my presentation will be mostly about the applications of the machine learning models. I will not talk about the models themselves. So there will be maybe a little lighter talk. So my agenda, a little introduction, then I will talk about the dementia reduction problem. This is the big issue in Japan and the aging societies in general. I will show you some of the examples of our applications and how we try to now move from the supervised learning into unsupervised learning, or maybe even weekly supervised learning, as we discussed yesterday in RIKEN. So basically, we are very open for the collaborations on the machine learning side. And also, I will show you some of our non-brain biomarker candidates, our collaboration will work now and what we try next. So this is our team. I am a member of the Dr. Otake Laboratory, CBAT team. So she is our team leader. Those are our members, like usually still in the Zoom connection these days. So we are the laboratory in which we design experiments, we conduct experiments, so we collect the data, we analyze them, and we also apply the machine learning models. So our main goal is to find neurobiomarkers of dementia. So we use the EEGs, and there are different devices we have in our laboratory. We run those experiments in the lab, but also we are now preparing home-based experiments. So anybody who would like to collaborate is very welcome, and we always look for the subjects. So our goal is to position our research in the so-called AI for social goods. So basically, this is already recognized in the world, and even United Nations put it in the goal number 3 of the sustainable goals, that elderly people really need support, and technology would be really fantastic to improve well-being and maybe delay dementia and all those problems. So there are many negative numbers. The numbers of dementia are growing. The societies are aging. Our bodies are living longer, but our brains have much more issue. There is no pharmacological approach. So all these pharma companies, they bitterly failed and there is no medicine. But as we know from the World Health Organization, there are quite many approaches which are non-pharmacological. We are changing lifestyle, changing diet, changing the way we live, and we can really support it with technology. So basically, when we look at the all the subjects on the problems. So around 60 to 70% of the dementia are so-called Alzheimer's disease-based dementia. 10 to 20% are related to vascular dementia, and the rest is like, around 10%. So basically, if we can cover monitoring both of those cases, Alzheimer-based and vascular-based dementia, we can really build quite good biomarker. And that's why we focus on the EEG, which is the electrical activity recorded on the skull level. So it's non-invasive method used in the clinics. And vascular dementia for the vascular system, blood system, basically we can use FNIRS. And as we know, there are quite many interventions, so the sooner we can do it, the better for the people. So as Lord Kelvin said already a long time ago, if you can measure it, you can improve it. And we know from the neuroscience that quite many candidates we can use. So basically there is a lot of background we can already choose. And some of those actually approaches are coming from the area of the brain-computer interface. So previously, before I joined RIKEN-AIP, I was involved in the brain-computer interfacing, and I can happily now use those methods now for the biomarkers of the dementia. And additionally, as I said, we also know that the vascular health is very important. So basically, bad vascular health is causes dementia. So that's why we are now developing the system when we can record together, and we have the system already in RIKEN, but basically due to pandemic, everything is a little bit delayed, but we can have also now use collaborations abroad and we can collect data. So the concept is to record together in the experimental setting, EEG electrical activity and the FNIRS. So this is infrared illumination of the skull. And basically we can monitor the blood circulation under the skull level. So basically two modalities together will cover around 90% of the possible dementia cases. So basically what is now, and we are a little bit stuck with the thing, so there is a problem with the labels of basically evaluation of people of dementia. So these days, the gold standard is the paper and pencil test, MOCA, MMSE, and so on. So even the latest publications very often refer to those tests. Those tests are very noisy, are very error prone because they are done by the psychologists. You cannot repeat them very often. So basically one score takes for 1 year, and basically brain could change very often. So what we really want to do, we want to use machine learning and completely skip those labels in this case. So unsupervised learning could be one of those our escapes. But let me show you first our results using the supervised learning. So the concept is to build home-based monitoring system. So you can see this elderly lady here watching TV. She's wearing wearable EEG, having iPad, and basically conducting this kind of mental test, which could be done every day even. So basically, like these days, elderly people monitor their health, like, heart health, by measuring blood pressure every day, etc. Now, quite often using different wearables, we want to add in the future this kind of brain tech wearable, which will really show if their lifestyle is improving their well-being, mental well-being, or basically maybe they can make some mistakes, and this will cause, call for some intervention. So the first classical paradigm experiment is coming from the brain-computer interfacing, the so-called oddball paradigm. So basically, we show the series of pictures. Before each series, we ask subject to remember one of them, so-called target. And we showed it in the kind of collection of the random presentation, 7 to 10 pictures. We can also ask subject to make a button press response, and we also collect behavioral responses. So in this case, when we look at the behavioral response, we can immediately see that our subject who are in so-called mild cognitive impairment, so this is kind of beginning of dementia, which we want to pick up as soon as possible to possibly switch any mental intervention. Those subjects would have significantly delayed reaction times. But as you will really see, those spreads are quite big, so we cannot use only behavioral responses because they are not very accurate for the classification. That's why we use machine learning, and this was our first collaboration with Dr. Chao and Chao from our AIP center. And basically, that time we applied the Tensor trained learning to actually see if we can classify those varying responses. So we know from the neuroscience that healthy people will have very nice so-called aha response when they see the picture which they memorized before. People who are elderly and shifting towards dementia will have this response of smaller amplitude and the delay. And when everybody ignores, this response will be quite flat. So basically in the BCI, there's always classification between target, non-target. In our case, we want to distinguish between healthy P300 response and this based related to the dementia or aging. So we review quite many machine learning methods, and the shallow learning method, SVM, linear LDA and so on, they basically performed just above the chance level. So it's not good enough. We use some Riemannian geometry methods, which were also like inspired by Dr. Min from our center, but basically they were around 70%. And the method which was proposed and delivered by the group of Dr. Chao, basically based on the Tensor trains, in that time performed around 80%, which is okay for the publication, but it's not still good enough for the industrial or basically healthcare application. So we are still looking forward and trying to push those results much higher, being above 90%. That's why we also tried the Riemannian geometry approach. This will be the work will be presented next month in Prague. And in this case, we can really see when we use the cross-validation, basically our data sets are not so big still. We can reach around 90%. But when we move back to the leave one out subject cross-validation, which is kind of more honest and the more application, in this case, our results really drop. So the problem is still related to our machine learning methods and basically very noisy EEG. So we also try some other methods. In this case, we try to narrow bound of the EEG, and this was presented in July this year at the conference at the EMBC, so one of the larger biomedical conferences. In this experiment, we ask our subject to remember facial expression, emotion expression. So basically, we have short videos of exactly same actor who is showing different emotional expression. And also as a reference, we can also use different actors, so this will be a more easy case. For that one, we use so-called analysis. So this is very famous in physics, but also in the neuroscience, analysis of the brain criticality. So basically, this is using the physical measures. In this case, we use so-called the trended fluctuation analysis, one of this kind of engineered method, which is based on the removing the mean value and then calculating the fluctuation over different time windows. So everything results into single coefficient DFA, but for the machine learning, we can use those scales, like our fluctuation coefficient over different scale. So basically, if we have 8 channels, from each channel we have 16 scales. So our feature vector will become 128 in the dimension in this case. And we know from the physics that actually DFA values characterize the signal as the anticorrelated and uncorrelated 1/f noise, which is kind of the most famous for the resting state, EEG resting state brain. We can have non-stationary and Brownian noise. And what we really see from our subjects, our MCI subject, those who move towards the dementia, usually have higher those DFA, in this case called coefficients. So we can tell them that those brains are more noisy. EEG recorded from those brains is much more noisy, much less predictable. But when we go back to the machine learning, we use all the fluctuation coefficients over different scales. We can really see that, again, most of our classical shallow learning classifiers would perform just above the chance level, around 67–70%. The best one would be random forest, and if our shallow fully collected neural network is also above the chance level. What is interesting for us here, we can really see that those pictures, videos we ask our subjects to inhibit, to ignore, they are better discriminable comparing to those pictures which we ask subject to attend. So this is really showing that for people who are shifting towards dementia, for them, ignoring stimuli is becoming more difficult and basically more visible in the EEG. So it's very good for us for the machine learning, comparing to those that they are still memorizing. So it's also quite nice kind of neuroscientific results, which we got from the results of the machine learning application. Another paradigm, we call it number 3 now, is called for the related to the reminiscence. So basically, elderly people have a preference for the interior subjects who are coming from their childhood. So for our Japanese subject, we prepare 4 sets of the interiors, like Showa era. This is the era from the childhood of our elderly subject. There will be more modern Japanese design. There will be also old Western designs and also modern Western designs. So we also asked our subject to evaluate those pictures. And immediately we could see that our paradigm was nicely designed because our Japanese subjects had really preferences towards the old Japanese designs. They didn't like Western, modern, old, or they were not so also happy with the modern Japanese designs. But what was more interesting when we looked at those preferences, when we put them in the 2 groups of the MCI subjects and our healthy normal subject, we could really see that we have kind of 2 kinds of the distribution in this case, that our elderly subject would be kind of more like, bimodal, so they would have positive and negative reactions, while the normal ones would have the kind of more balance. But again, those behavioral responses are not as good for the classification. When we look at the EEG, again, in this case, the data set was not fully balanced, so chance level was around 60-something%. And again, we could really see those results, that those pictures which we asked our subject to ignore, they were the best classifiers. In this case, fully connected neural networks was the best one, together with the random forest classifier. And this is our latest, one of the latest paradigms, which we design now in our collaboration with French and German consortium. So we have trilateral project, because in the 3 countries, the aging is becoming really a big issue. So in this very fast presentation of the images, one of them again is memorized, shown before the paradigm. And we know that in this case, so we also can collect FNIRS and have different patterns of the blood oxygenation. But what we really see in the EEG, when subject remembers something, they would have this kind of different reactions comparing to the ignored picture. So the blue one would be the reaction when sometimes it's flashing this known picture. When we show control, there would be exactly the same reaction. We can also compare different systems, and our dry electrode system is the best one. So this is our latest purchase. So this one is kind of a little bit colorful, the collaboration, because this data we're collecting now. And we are very much inspired by the latest, results from the Wave2 vector application. So basically, this is self-supervised learning coming from the Facebook, and they have beautiful this application when they compare EEG or MEG together with the speech. They use it for using nested constructive learning, and then they can distinguish to which speech the subject is listening. We now work on this one to make this exactly same application when we show this video presentation, so we can really use videos as time series, which we will connect with the brainwaves, and hopefully through the contrastive learning, we can classify healthy versus normal, or even having some regression results. So the final experiments we're also running is related to the learning of the new skill. And this is for our elderly subjects. We train them to recognize emotions. And usually we use some semantics as a description of the emotions. In this task, we ask our subject to learn kind of 2-dimensional grid of the arousal and the balance. So this method is used by the psychologists, but it's not common among usually adult people. So in first step, we show short video with emotions, then we show where such video is being categorized on this 2-dimensional grid, and then we ask subject to put this result. So basically, it's kind of copy and paste learning. In the final step, we show again different series of the videos, but this time we ask them to kind of try to categorize them based on what they learned 5 minutes ago. So this paradigm is testing short-term memory, so-called implicit procedural memory, which is kind of still very strong with the elderly people, is preserved in dementia. Also spatio-temporal memory, so this would be a little bit weaker with dementia people, and emotional recognition, which is usually also again preserved in the dementia. So let me show you some results. So again, when we look at the behavioral results over different scores of our cognitive score from our subjects, so that are made psychologists, we can really see some linear fits, but those features are really noisy, so they cannot be very helpful for the machine learning. When we use the trend and fluctuation analysis, so this kind of complexity analysis of the signal, we can really see significant shifts, mostly in the temporal areas. So those are the areas when dementia usually starts. We can really see significant differences, and basically, again, in this paradigm, we can see that our dementia subject or MCI subject have more noisy signals comparing to the healthy normals. So again, when we use those parameters for the classification, for the machine learning, and this is for us very nice results, because we can reproduce very similar results for the training of the subject and then for the testing. So basically, again, 2 favorite classifiers, random forest and fully connected neural network, scored about 85% for both cases. And as I will see, those results are reproducible over different paradigms with exactly same subjects. So this is, during pandemic, we couldn't collect any data. We are completely in the lockdown, but luckily with the collaboration with Poland University of Nikolaus Copernicus in Toruń, we could record new data because they don't have any restrictions anymore for the collecting new data. So basically, we reproduced our paradigm. First, 3 years ago, almost, we used it in Japan, very simple wearable. So the results were quite noisy. Now, when we switch to the better wearable EEG, we can really see that our features improve dramatically. So again, We can do machine learning with the simple, in this case, because data is much better now. And we are now preparing back in Japan after the restrictions to run exactly the same experiments. So this is our first step to move into unsupervised learning methodology. And in this case, we try the UMAP, like uniform manifold approximation mapping, which basically is unsupervised clustering. And when we really see for our first data from the low quality wearable, it's very difficult to actually see any separability. So this is like projection of the two first UMAP dimensions. So the blue dot would be for the MCI subjects, orange dots are for our normal subjects. But from the newly recorded data in Poland with better quality, also 8-channel wearable, we can really see that already UMAP can very nicely separate those two groups. So basically, this is very good also pre-processing we can use now for our machine learning steps. So this is very good for results. We also quickly tried using some variational autoencoders, which basically we use for this latent space for our feature extraction. So basically very simple, in this case, autoencoder, having only 2 layers of the input and also 2 layers at the output. So we can train it very quickly. And again, we can really see our noisy recordings, pre-pandemic recordings, are really difficult to be separated. Those are, again, only 2 projections of the 2, like our latent space. But when we look at our newer data, the separability, again, is becoming very beautiful. Again, data set is small, it's a little bit overfitted, but it's really showing that we can really start moving into unsupervised training and maybe use later on our methodology as also research tool. In this case, we do it for the binary cases, normal versus MCI. Next step would be more like regression, because we can have different levels of the cognitive scores, and we can really see how this data will be in this case in the regression model represented. But so it's very very nice. And if somebody would have also better idea, we are very open for some new suggestions. So this basically, again, the plot in the 3 dimensions. Again, you will really see our noisy data is really stuck together. Our new data is beautifully separable, so this is very nice pre-processing for our machine learning. So this, what I already mostly was speaking before, it's about the brain waves, so EEG recordings from the brain. But also we try to use other modalities, and this is one of the experiments Dr. Otake, our team leader, is conducting with elderly subjects. Those are the so-called conversational analysis and conversational intervention. So basically, our elderly people are coming to our laboratory to having kind of small conversation, kind of social interactions. So we are recording them with permission of the elderly. Then we can use machine learning to analyze those conversations. So basically, in this case, we are using classical wave-to-wake approach. So basically, we use the pre-trained model to in this case, analyze our speeches. All the speeches are analyzed separately. So for each speaker has own, in this case, vector. And then once we transfer everything into wave-to-wake, we can check what are the topics that each subject is jumping between. And we can really see, we call it conversation pathway, how much within one conversation, which takes around 5 minutes, people are staying on the topic or very much switching between those topics. So this is quite interesting because we can really use machine learning model as an analysis tool for the speech dynamics. So we can really see between different parameters, there are some linear fits. But when we look later how we can predict their cognitive scores, it's becoming quite interesting because we can really see that there would be significant difference between those pathways, although those lengths of the pathways are quite noisy and quite spread. But when we look at our results, our regression, we can really see that we can predict quite nicely ±2 in this level of those cognitive scores based on the speech behavior in its conversation. So this is the work we want to finish and push for the publication. For the moment, it's on the MEDAR high. The other in our collaboration also going for this biomarker of the mental diseases and also the dementia is collaboration with the Okinawa Institute of Science and Technology. Our colleagues Zahari Taufik and Professor Takahashi, basically they developed beautiful, very new method that they can analyze the proteomics, so basically the information, what kind of proteins they have in the synaptic clefts from the healthy and living subjects. So previously to do such analysis, they had to have the brain sample of the subject who already passed away. They could use it post-mortem. In their new method, they are using stem cell technology. So basically, they take the blood samples, they grow new neurons, and basically they can, those kind of artificially grown neurons, they can analyze basically synaptic connection for the proteomics, in this case, information. they can identify up to 5,000 proteins. So it's really beautiful multidimensional data. And what we really try to help them analyze this with the machine learning in this case, and using also in unsupervised way. This is an example from the UMAP, when we try to separate those, for the moment, still binary versus healthy versus schizophrenia, but basically quite nicely showing how we can already implement AI in the very early stages for the research. For them, it's very important to, as quickly as possible, analyze which of the protein candidates are the best for the analysis, because later on, they can search for lower number of the proteins, even they can find 5,000. So this is ongoing, but it's quite interesting how we can quickly plug in AI and the machine learning in the research of the new, in this case, biomarkers. So basically what next? Sorry, I am going really fast, but we are in this consortium of the German, Japanese, and French, in this case, project. So basically on the French side, we have INRIA and this Alex Granford, Professor Tojo from University of Freiburg, and basically we try to develop together let's say international team for the collecting data, but also for the analyzing and providing as soon as possible viable biomarkers for the healthy aging and dementia. We are also now implementing our international, in this case, experiments, which we can conduct them in Poland, Germany, France, and Japan. We have this nice small robot developed by Professor Dr. Otake from our team. And basically, this would be a combination of the robotics, visual stimulation, audio, and also other modalities. And basically, we really hope that this will progress into kind of new development of the easy wearable that everybody can use at home and evaluate mental fitness. Thank you very much. And if there are any comments, I would be happy to answer questions.
Okay, thank you very much, Tomek. So are there any questions?
Questions from EPFL side?
Or suggestions, comments?
I think it's a very important application, yeah.
So yes, let me start from a big question. So sure. A few pages back, you had the regression experiment result.
Okay, sure.
With the straight, yeah, this one. So if I see the data on the right-hand side, so these are extremely noisy.
Yes,
and
yes.
Of course, you can take some tendency of data, but prediction may not really be, may not really make sense in this noisy setup.
So, yes, so that's why, this is still work in progress, and we really would like to improve it. But basically, you can do it +-2 on this mental evaluation, which is quite okay, because this is as close as quite often psychologists are also making similar errors. Oh yeah, I do agree. Trend is quite interesting, but the result is still not publishable.
But does it really make sense to try to make some prediction from these extremely noisy data set?
Yeah, but practically this is super interesting, because from the speech for the conversational behavior, we can try to predict +-2. So it's quite, I think it's quite good candidate.
So from this noisy data set, we may say okay, one data set is different from data set in some tendency. We may draw this kind of conclusion, even if data is noisy. But if you want to really make some accurate prediction, then already the data is noisy. So then there's no way to have accurate prediction. That's a limitation of the not the limitation of the method, but the limitation of the data set problem.
Sure, I agree. But in the future, we will have multiple recordings for this conversational behavior, brainwave, and so on. From such, this would be one of the parameters we can use.
Yeah, so you need a lot of effort in improving the measurement system device or measurement
basically, because this is speech, so this is from the conversation, so this is on a completely different side, we don't use EEG. I believe EEG is the best one, candidate, This is using speech behavior, so this is analysis of the topic of the conversation.
Okay, thank you very much. Any other questions?
May I ask a question?
Yes, of course.
Yes, I'm Kenji Doya from Okinawa Institute of Science and Technology. I'm very glad to know that you have an active collaboration with my colleague. Yeah.
Yes,
And
I'm very happy.
Experiment. So the proteomics from the blood sample of the subject, does it reflect the genetic predisposition of the subject or pathological state of the subject?
I think it's more like pathological state of because this is expression of the protein. So this is related to the DNA, but basically based on the expression. So I think it's the pathological state of the subject.
Or even though it is blood, not the brain sample. Still,
But, you know, okay, but from the blood, that growing stem cell of the neuron. So basically, they have artificial neuron, artificial in this case, synaptic cleft, which is grown from the blood sample.
yeah. But even genetically twins. So some of them become pathological state, some will stay
Yeah, sure.
pathological. So environmental effect is also important.
Yeah, but I hope that already in the blood, this maybe is already included.
Okay.
Because so this is question to my colleagues. Basically, we do machine learning, but they believe that this is quite good, like information. Because blood sample is taken already from the maybe genetically modified.
All right. So I asked to adapt this.
Sure. So ask Zach, like he is like professional.
Thank you.